Okay, good afternoon everyone. I'm Ash Gawthorp, Technical Director at the Test People. Thank you for joining this webinar where we're going to discuss some of the key challenges in developing and testing the performance of mobile apps and some of the concepts that need to be considered. I'd like to thank everybody for joining this afternoon. I'd also like to thank eSynergy and particularly Adele for the opportunity to present this. Just a few housekeeping notes. We'll continue through the slide deck in a minute and the points. If you could mail any questions that you have as we're going along, Adele sat next to me will be able to take a look at those and answer those. Hopefully we'll be able to answer as many of those as we can in the webinar itself. If we can't, then we'll take those offline and we'll follow up with you from there. Anything else to add, Adele, in terms of housekeeping?
No.
No? I think we're good to go. Okay. So just a little bit first of all about Test People and myself. So the Test People, we're a technical testing consultancy. We were founded 7 years ago. Initially 4 of us. We've grown fairly significantly. Now we're up to around 150 with offices in Leeds, London, delivering solutions to clients in the UK, but also clients a bit further away in the US. We're a professional services company. We work right the way through the testing disciplines, testing, test strategy creation, automation, performance testing, including high-level consultancy and some of the assurance aspects through to standing up test functions and actually delivering testing as a managed service. We are tool agnostic. We're going to be discussing a few tools and a few approaches on this call today. We use all kinds of tools in our client engagements, open source tools, commercial off-the-shelf tools. We also have our own internal R&D teams who develop custom tool sets and capabilities that we require in order to fulfill our clients' needs if there isn't anything available on the market to do that. Sometimes this is to support cutting-edge technology, sometimes it's in fact really old tech that the current tools don't support and won't support. We have training in terms of all aspects of testing as well, which is really a delivery of part of our graduate academy training program, which we can deliver internally and also to clients. So I'm not today going to reference directly any clients we work with, either working with now or have before, but we've worked with several hundred clients over the last few years, and over that time that's allowed us to build a fairly comprehensive picture of what goes well with respect to performance testing, what doesn't go quite so well, and where we've done performance testing with them, some of the transformations that we put in place, really how that went. So what we're really wanting to do today is to share those insights with you, share our kind of understanding in terms of where we're at with performance testing. So just a very little bit about myself. I'm actually a hardware engineer. My degree's in electronic engineering. I started out working for a 3D graphics company. Initially working as a hardware engineer and then found myself writing software to test the capability of that 3D graphics hardware. Then moved into software development in financial services before working for an American management consultancy company implementing performance testing solutions and performance improvement solutions before we founded the Test People. So in terms of what I'm going to run through today, looking at the list of the attendees, we've got a very mixed audience. We've got a kind of full spectrum of skills, experience, and expertise. So on one end we have business and product owners through QA professionals looking to move into performance, mobile devs wanting to understand more about performance, right the way through to seasoned performance testers just wanting to look at sort of any insights or any improvements that we can make. So that's quite a broad spectrum of people we've got on this webinar. So what I've tried to do is tailor this to try and give everybody something really. So for some of you it's going to be a little bit straightforward, and apologies for that, but I really wanted to get everybody up to speed so we can build on that. So, first of all, I really just want to look at a sort of simplified mobile application environment. So what the components are and what makes it slightly different to normal apps. So, if everybody can see the diagram there, just to look at the components. So, we've obviously got the mobile device. Then got the you've got the handset. That handset communicates with a base station and local infrastructure from a wireless point of view. You then have that going out to that cloud that I have omitted to label, which is actually supposed to be the public internet. And you then hit the server-side infrastructure, and the third, the actual infrastructure which is serving the data that's required by the applications itself. One thing I've omitted on there that's greatly simplified, we often have a lot of third-party systems also talking to the app. Payment providers, for instance, data services, all of these are providing data that's required ultimately for the mobile app to provide the service it needs to provide, and all of them need to be considered as part of performance testing. Okay, so sorry, 1 second, slides are slightly out of order. So one thing that we tend to do, we tend to split the data into the data that the app requires into subsections in terms of what it's used from and where it actually comes from. So irrespective of the application type, we generally find that there are 3 types of data that we need to consider, and they all need to be considered separately. So we have data that's required to build the application. So in the case of a hybrid app or a web app, this is CSS, JavaScript, images, static config data. 1 second. Oh gosh. Move that out of the way. So the application needs that. If it's an actual native mobile app, and that's from the actual app store itself. We then have data which is broadcast to everybody who has a particular interest in it. So this is sub-data. So for instance, price updates out to everybody who requires them to subscribe to a particular instrument. News updates to anybody that subscribes to a particular news channel. Now that is pushed to everybody that has subscribed to a particular channel that has taken an interest in it. So it's very dynamic, it's changing rapidly and regularly. Crucially, the users aren't requesting this, it's actually pushed out to them. And the third part is the private data that's essentially the request-response data between the user and the particular server interaction. So when you're logging in, when you're accessing account information, when you're performing a transaction. So if we just go back to the diagram a second. So what I'd like to do is just consider what affects performance for a minute. So starting from the beginning, you've got your user who interacts with the app. For instance, they log into the application. And I also, for each one of these components, want to consider what's under the control and influence of the actual organization that's producing this application, and so therefore can be tuned, can be modified, can be optimized, and what's outside of the influence of the organization producing the application, but the system can be designed and implemented mindful of that to be as optimal as it can be. So we start from the beginning. So you have the client-side application. So this is largely under control of the vendor creating the app. How well that's written, the choice of technology used to implement that application. All these have an impact on how well the app performs, whether there are any delays in rendering any of the data that comes back. So you then have the handset itself. Now, this is absolutely outside the control of the application creator. So, and you have a widespread. So with iOS, you're limited to a few devices. With Android, you could be running on a 600-pound tablet or a 60-pound tablet. And the performance capabilities of that device vary drastically. So the end user experience is also greatly enhanced or greatly degraded by the capability of the device that they have. So that needs to be considered when you're designing. So that device, for instance, when you log in, sends messages. So those messages, the question is how many, how big. Efficiency has a big part to play here. So how much data gets uploaded and downloaded, so that's the requests, response, the size up, size down. As a rule of thumb, it's always slower to upload than it is to download. The base station that's there, that's not under the control again. And the public internet, definitely not under control. So the number of hops between in that cloud from the base station ultimately to the data center serving the data, the distance, the bandwidth that you're able to get, all of these have an effect and an impact. So the server side, you then have to consider how long it takes to respond. Again, this is largely under the control of the app vendor, although it depends where it's hosted. It could be that it's hosted internally. It could be it's hosted in a IaaS sort of service. But essentially, the efficiency of the server-side code, the number, the capability of servers at each layer, how quick the SAN is, database, speed of third parties, they all play a part. But that's largely the case, and always has been the case for any web app, and doesn't really differ for a mobile app either. The message then comes back. So pretty much a repeat of what we had before. So across the web, into the ISP, out to the local cell, into the device, and then you have the processing time of the app to render and display. So at that point, you're then successfully logged in. The app is then going to request more information, so you have a repeat of that information. In the case of the Type 2 data that we saw, there's no request required, so the updates are pushed when they're available. So there can be much more complexity there. You can have other content providers which are closer to the actual user to deliver content delivery networks, for example, but largely that's kind of it. So the key points there, the handset isn't under the control of the person that is, or the organization that's writing the app. The application running on the handset is. The actual mobile communications itself isn't, the public internet isn't, the server side is, and third parties providing data into that server side infrastructure are TNS. So one thing we often find ourselves doing is trying to optimize that bit in the middle that we don't actually have the control over. So whilst we can't actually modify the time that it takes to pass a message and to receive a response over the public internet, we are able to design apps and to modify apps so they are mindful of it and optimized so that they are limited, so the performance degradation is limited as much as possible. Is there any questions coming in? Okay. Yes, we are. We're still on the so SEMA. Yes, we're still on the web app, hybrid app construction screen. No, we're back to the yes. That's right. Yes. Yeah. Okay. So that kind of so far we just kind of described what happens when you have one user using the system. So that's the performance that the end user experiences on their device. As a result of the message flow through the system from the mobile device right the way through the server and back again. That's one user, and that's very important because obviously if that performance isn't optimal, if it degrades, then users are going to vote with their feet potentially, or at least they're going to question their use of the application. So we mentioned data distribution there in terms of what you can do. So one solution that we often work with our clients on is around taking the content that needs to be delivered to a particular user and getting it as close to that user as you can. As we mentioned, you can't really you can't speed up the public internet, but what you are able to do is to move some of that static content closer to the users. So rather than it going right the way across the public internet and a non-optimized network to retrieve that content, it's actually going to a local edge server to retrieve that content, so it's much closer to the end users. And that's what the diagram that you can hopefully see there essentially. So you're uploading data to an origin server. That data is then automatically pushed out to a number of edge servers, which are geographically located close to users. One of the key points to consider is that the network connection between the edge servers and the origin servers is optimized as well. So that is as quick as it can be. So the only part you're actually having to worry about is the connection between users and the edge server over a non-optimized network. In actual fact, a lot of edge servers are provided within ISP's data centers as well, so you're actually not even going out over the public internet in order to retrieve some of this content. So we talked about performance of a single user, but what happens when you have multiple users connecting to a system? So the only point that changes here is that really the server side is having to do more work. So the more requests that are made, the more updates it needs to push out as you have more and more users connected to the system, the more and more work the server-side infrastructure is having to do. What you find is that you can load a number of concurrent users on the system, and the response times to return that data will still be within acceptable limits. But what you find is that when you start to reach a bit of a tipping point, is that you start to see more and more errors returned, but you're still probably at a stage where you can back off the number of concurrent users on the system, and the system will return to normal. You start to exceed that, and you're then in the territory where the response times that users see elongate, so their end-user experience degrades, but also you reach the point where you have an irreparable system failure, essentially, and services break, applications break, and effectively the system is then down, and you have to take action to fix it. So the key point there is that really there are kind of two aspects to performance that we need to consider. There's the performance of a single user connecting themselves and their end user experience from the point of view of how long it takes for key business processes to take, how reactive the application is, how quickly the updates are coming through. But you also have to consider what happens when you have many users all connected to the system at the same time and how the server side degrades. So there are two kind of key approaches that we've got here. So the first approach that I want to mention is what's defined as a protocol-based approach. So this is what's often regarded as traditional performance testing, essentially. So how this works is, and there are lots of tools out there that do this, both commercially and open source. So the client interaction is recorded within the tool as a script. So you script the key business processes that are deemed to be in scope of the performance testing. The scripts are then parameterized and correlated, so you end up in a position where you're able to replay those scripts, essentially. You then orchestrate those scripts and execute them in accordance with a transaction volume model or load profile, which dictates how that system will, how the load will increase over the duration of the performance test. But the key point here is that the script is a functional simulation of the actual client. You aren't actually using real client. All you are doing is creating a mimic of the real client. So from the server side's perspective, it sees network traffic, which is equivalent to having a real client on there. So this has been used for years, decades, this approach really. What's good about it is that it allows you, with very little infrastructure, to be able to quickly mimic tens of thousands, hundreds of thousands of concurrent users, all interacting with the application. And crucially, you're able to see how the server side performs. So you're able to see how the response times that those requests create, how they elongate over time, any errors that are produced. What it misses and what it doesn't give you is that view of the actual end user experience. It gives you an indication of how long the network responses take, but it won't tell you how long it takes before you actually get a login response back on the client application. So there's a secondary approach that's been used more of late as well, which is actually using the real client. So this, instead of using a network-based simulation of the actual client, you're using the real client. You're actually driving the client using automation techniques. This allows you to leverage any pre-existing automation assets that you have, which can be quite useful if you have those already. And it records that true end-to-end transaction response time. So you're not seeing actually just a sort of synthetic view of how network traffic responses are elongating. What you're actually seeing is how long it takes for a particular message to be rendered, or a price to be rendered, or a news update to come through. The downside is that it obviously requires a lot more hardware. You need a lot more emulators, you need simulators running to be able to actually use this and perform at higher load levels. It's something that we do use for various web technologies where the client technology makes it very difficult to use protocol-based performance testing. But what you can do is you can use a hybrid approach where essentially you're using protocol-based testing to do the heavy lifting on the server side, and you're using client-based testing to get that true end-to-end response time and actually understanding how your end users actually experience the system. So, question for people on the call, really. It'd be good if you could just respond with, for those of you that are doing performance testing at the moment of mobile apps, or indeed any other form of app as well, how many of you are actually using a traditional kind of protocol-based approach, using a traditional tool, and how many of you are using a approach which is which encompasses actually the clients themselves? Now, this could actually also be, in terms of mobile performance testing, actually manual testing that you're doing as well. So you're manually testing the application to kind of check the response times and to see those, or it could be instrumented automation tests that you're using to actually capture those results on either real devices or simulators or emulators. So I'll just leave that with you for a second, and we'll respond on any questions that come back from that. So a number of you have asked about performance test tools, specifically around open source tool stacks, around commercial off-the-shelf tools, in terms of what's out there, in terms of what works, what doesn't work quite so well. And our kind of response to that, having worked with a lot of these tools and worked with a lot of clients that use a lot of these tools, is that the most important aspect to actually get right is that the tool that you use is the right tool for your organization. Now, that's a combination of a number of factors. So that's a combination of the skill sets that you have within the test teams themselves and possibly within the development teams. It's a function of the technology that you're using to actually create these applications. It's also a function of the number of users. A lot of the tools, they charge based on the number of concurrent users that you're wanting to use. So if you have a user base of several 100,000 concurrent users, for instance, that's going to make it very expensive to use some of the commercial off-the-shelf offerings that exist. For a number of the kind of automation tools, there's a question around how close you are to the source code. A number of them require you to change your build process. They require you to build libraries into the tools in order to make them automatable. Some of them that don't use that approach, some of them use image-based matching approaches, which can work quite well, but at the same time can also be quite restrictive and can also make the system and can be a little bit more brittle than some of the other techniques. But the one thing I would say, the overarching point here, is that it absolutely needs to work with your actual application. We've worked with a number of organizations where they have chosen particularly a commercial tool and they've invested heavily in it, and it's proved reasonably successful, but then they've come across some showstopper, some issue down the line where the tool is not able to work with their system. So for the commercial off-the-shelf tools, I strongly advise that when you're speaking with the vendors that you actually get them to work with your application. your app will have its own nuances, it will have its own quirks, it will have its own foibles, it will have its own challenges. It's really important that the tool vendor demonstrates that their tool can work with your app rather than a demo application. So, in terms of the open source tools, I mean, there's a point there around considering the full cost of open source. So open source are free, or free to download and free to use, but often the time that needs to be invested in them can be pretty significant. The tools are often very well written, but the documentation is often very light. Or you sometimes find that the tool is written for a very specific purpose and doesn't extend necessarily to what it is that you're wanting to do with it. But at the same time, that's actually a feature. If you have in-house dev teams, then it could be that you can actually extend that tool and extend the capability of itself. On the other side of the coin, the commercial tools, they tend to be much more of a sort of turnkey solution. You will get support. They'll be able to provide training. They often have more polish, but the slight downside can be that if you invest in a tool and then you elect a choice of technology which isn't supported by that tool, then you're at the mercy of their product roadmap and trying to influence them in order to adapt it to your needs. It has to be said though, some of them are much better than others. There's a lot of the smaller vendors out there who are actually very, very reactive to their client requirements and quite quick at turning around changes. So in terms of just mentioning a few names, so protocol-based, in terms of commercial solutions, well, it's definitely worth looking at solutions from HP, Sosta, Neotis, SmartBear, IBM. There's a whole host of them out there. They all offer free demos. You will be able to download it for free. You'll be able to, if you're interested in just developing your own professional experience, you'll be able to have a play with it. You'll be able to try it against a number of applications and see how well it works for you. In terms of protocol-based open source tools, we have used and continue to use JMeter quite a lot as an open source offering. It can be a little bit quirky sometimes. It doesn't do everything, but if you have very large user volumes, because there aren't any license restrictions around it, obviously you can execute as many concurrent users as you require there. In terms of the client base of automation tools, so again, commercially available, Eggplant, Sosta, Jammo, Ranorex, MonkeyTalk from Gorilla Logic, which I guess is somewhere in the middle because you can again download that or charge you for support. All of these offer very good solutions, but you need to be, again, very mindful of your application and make sure that these work with your application and that they fulfill your needs. Particularly if you're in a scenario where, in the case of some of them, you don't have access to the source code. If you have another party that's producing the application for you, for instance, commercially they're not able to modify a build to be able to build a set of automation libraries in there, for instance. That very soon strikes a few off that list because they do require the app to be modified in order to be able to test it. In terms of open source tooling, Appium is out there, pretty effective. I mean, there's a question mark around whether it's really ready quite for production use yet in all aspects of what it's there to do, and it can be tricky to set up and configure. But once it's running, the framework is good. We had any feedback on? So point here. Okay, so feedback there. So currently some people using API level scripts for most performance testing, automation at the UI level, but for functional testing. With spot checks anecdotally applied. Yeah, a few guys doing that. And again, yeah. So a few people also offering up a number of open source suggestions. I mean, there are lots and lots of them out there, and they're changing on a weekly basis as more and more offerings come along, more and more are added. the question there is backing the one which kind of works for you. They tend to get quite a lot of community support at first, but then sometimes they kind of sometimes they go away. Sometimes you find somebody else will produce a tool which does exactly the same thing virtually, but that will get a lot more support and that will continue. So it's really a question of which horse to back in that scenario. So not there. Yeah, I mean, so in terms of the so can everybody hear me? Okay, sorry, I think I was muted there for a second. So one key point that a lot of you asked was before the webinar was how do we actually take performance testing and how do we actually bake it into the solution? How do we actually fit it into our software development lifecycle so it's effective? There were a few questions saying that it had been done, perhaps been done too late in the process, that they weren't getting the value from it. So there's a few points to make here that we've seen over the years across different clients in terms of key things that we've seen that work well and that tend to give the good results. So let me go through some of those. So this first one is absolutely critical, really. Where we see failures in performance tests, this is normally where it goes wrong. The fact that nobody has up front defined the non-functional requirements for the application at the design stage. They're often very clear about designing functional requirements. They'll be defined very clearly, but nobody has actually defined what the application should do from a performance point of view. There are other non-functional requirements as well, where it tends to be performance where this really manifests itself as a problem. So what that means is that the application gets developed functionally, a lot of investment goes into it. Performance testing is done either at the end or often never until there's sometimes a performance problem that's experienced in live. But what you find is that you're then trying to go back into the application and you're trying to improve it, often where it's actually not often where the application is actually not being designed to be able to meet those performance characteristics, or in the case where you have a fairly complex commercial agreement with a third party who's providing that software to you, for instance, they can actually, they are not commercially obliged to make those changes for you because they weren't spec'd in the first place and they weren't asked about. So often that can lead to quite a lot of problems further down the line. In terms of establishing them, a few pointers there. Often when you ask business people, when you define them and say, for instance, what should my login time be, they may come back and say, well, it needs to be in under a second or something, which is pretty unrealistic. That needs to be an open discussion between business, between dev, between test, between infrastructure, between everybody that's actually employed in coming up with that solution, so that unrealistic targets aren't set, and if the business actually requires those targets to be set, that they are aware of the cost and time implications of the engineering effort that's going to be required in order to meet that. So we've got a question here, given the number of factors that can affect performance of a mobile app device, network provider, public internet, how do you advise defining performance requirements in the spec? It seems that these might be different than a browser based on a desktop-based application. I think so that's a good question. So the first thing to do there is actually look at the user base and actually determine whereabouts the people are. So we work with clients where they have a distributed user base around the world, for instance, in one example. So you have clients in Europe, you have clients in North America, you have clients in Asia, you have clients in Australasia. So what you can't do is you can't actually, one size doesn't fit all in terms of those requirements. What you can do is you can kind of group them by region and say, these are the performance targets and the performance characteristics for this particular region. Also, things like CDNs that we mentioned before, enterprise messaging solutions, where you're able to distribute servers around the world to get content closer to where the users are. that can also help drive those response times down. But nonetheless, by having that conversation up front and setting them up front, you can kick off that engineering. Hopefully that's answered the question. If it hasn't, please just ping me back, or we can take it offline. So the next point here is around reviewing the application as it's being developed. And one thing that we do quite a lot is before we actually try to apply load to a system, we'll actually just look at the messaging going backwards and forwards between a client application and server. And what we often see is that when you actually lift the bonnet and you look at what's going on under there, that you see that there are lots of requests that are being made backwards and forwards, and some messages that are perhaps being sent unnecessarily, data that is being requested that isn't needed, caching that isn't optimal. There are a whole host of issues which aren't immediately obvious to the developer. It's not a functional defect, but you know will affect scalability and will affect performance. It needs to be regular, because it's not just the case as well that it can be performed once and then you never raise it itself again. I mean, we come across scenarios where you, for instance, with hybrid apps and web apps, where you have where the data is, the good practice is applied, JavaScript is minified, it's concatenated to reduce the number of round trips, for instance. But that's done as a deployment activity. That's done post the dev team. So if that isn't applied, then you can suddenly go from a position where you have a reasonable number of JavaScript files, for instance, to suddenly one where you have several hundred JavaScript files and a whole load of debug libraries in there that shouldn't be there. So it's important to keep checking that as you go along. Once you do have performance tests in place, it's important to run them as regular as you can and actually sweat those assets. Not just when new features go in, but also regression with each release as well, just in case something has crept in. If the front end hasn't changed that much and there hasn't been that much functionality added, then in actual fact the impact of that should be relatively low, as with any luck the actual effort required to rescript will be greatly reduced. So we mentioned around there's a question there around geolocations. This is an interesting one. This next point here. So if you're actually performance testing, if you have a client base which is spread around the world, for instance, what you can actually do is you can actually either test from infrastructure, a number of solutions would like to test from infrastructure which is spread around the world, or actually simulating in a controlled environment what those network characteristics look like. So you're able to say, you're able to dial in essentially the latency, bandwidth, packet loss characteristics that you'd expect to get from a mobile network accessing the system from Australia, and run your end-to-end performance tests against that to determine the impact on the end user experience of running it from that particular location. What you're also then able to do is you're able to play with a number of these sets of network characteristics, and that allows you to build a picture of how susceptible your application is to, say, increases in latency, for instance, which can be quite insightful and which can then help with some of the performance tuning effort in terms of where you spend your budget there, in terms of making it quicker. Final point here, so running continuous or regular performance tests in the production environment. Now this isn't necessarily to everybody's liking, but we've worked with a lot of systems where the performance test environment just isn't quite as lifelike as it should be. Now sometimes that's by design, sometimes that's for cost restrictions, sometimes that's because of configuration management errors and configuration management issues, which mean that whilst the performance test environment works functionally, to a non-functional point of view, it isn't representative of life. Now this can be done either from either a time when the system is down or a time when the system is very quiet, for instance. But by running that, it gives you an extra level of assurance. And also, when the system is live, if you're able to run those user journeys at a low level of concurrency, then that also gives you an insight into your live performance as well. Question here, so working in agile environments, how do you fit in performance? So that's a good point. I think there's a question around, which unfortunately we can't include for time restrictions, but there's a question around the scale of performance tests. So at one end you have your kind of big performance tests, which are the all singing, all dancing, include absolutely everything in the system that's required, third parties, representative infrastructure live, full user volume testing, full integrated tests. They often take a long time to orchestrate, and they're often very tricky. But if you're working in an agile environment, what you can do is you can even just add some instrumentation and measurement around the time that your unit tests take to execute. So what that would allow you to do is that it wouldn't allow you to see if there were how the system would perform end to end, but it would allow you to see if you'd introduced any regressions. It would allow you to see if there are any significant issues that have crept in. Because one of the challenges is if you have a number of sprints which then go into a large sort of performance test at the end, you could have checked something in several sprints back, which could have a major impact on performance. But if you don't get to see it till you do that large integrated test at the end, then effectively you're having to unwind quite a lot to go into the beginning again and rerun that, or instrumented automation tests as well, to be able to run those and to user acceptance tests to get a view of just how quickly those sort of key business transactions are taking, and whether they're elongating over time or whether they're reducing. So ideally doing something every week. I mean, there are large organizations that do that actually are able to run performance tests as part of effectively as part of their CI build, so they're able to kick off a full integration test on the back of that regularly, but they're exceptional, and that takes quite a lot of investment in order to get there. So question around how to measure accurate performance when the applications be run on different devices. So that's an excellent point. So in terms of, that goes back to the point I think we made in the first slide, you have a huge difference in capabilities across the devices themselves. You have other things to consider around the version of OS. There are settings that users can put on there, for instance, that can make a difference. Actually going with something which is building a matrix of a set of devices, varying between the fairly cheap and fairly kind of low-powered up to sort of fairly hefty devices, allows you to kind of build a picture of that and kind of see the extremes that we're talking about. I mean, there is either another question here, which is in terms of actually the application that you're wanting to design and the application that you're wanting to run. If you have somebody that's connecting over a very powerful Android tablet over a 4G connection from the UK versus somebody that is connecting from somewhere in APAC over a mobile network on a very cheap Android device, for instance, at some point there has to be a realization as to whether you can deliver the same application to them both and expect it to work. Sometimes you need to consider whether in fact you need a cut down version of the application for those particular scenarios. So in terms of iOS, so really the protocol-based performance testing, the approach is the same. You have the device which you plug in. You're then able to record the scripts. You're able to correlate them, parameterize them from a server-side perspective. From a client-side perspective, you're in that similar position of actually instrumenting and running tests on the real device. So I just want to touch, a number of people were asking just kind of around before the call on optimizations in terms of what can you do. There's been a lot of discussion around the actual messaging going backwards and forwards across the public internet and what you can do to improve that. You can't speed it up, but what you can do is make your app less susceptible to latency and issues. So a number of key sort of overarching points here really that we kind of taken on board. So less is more. So less means fewer round trips. So that's combining assets, CSS, JavaScript, images, optimization of the data received. So in terms of minification, caching. If you need something, get it and get it once. Don't get it again every time. When key challenge we see, HTTP, currently you're not able to compress headers. So you're able to compress payloads, but if you have a very large header, that has to be sent through. So one example that we saw, which was it's actually a foreign exchange trading system, there was a price update which needed to go out, which best case scenario should have been 20 bytes or so if it was actually pushed across a half decent data connection, but in practice it was 1.5K up and 1.5K down. So that's kind of two orders of magnitude greater for exactly the same amount of information. Keep the user informed. Sorry, closer is better. So we touched on that again. This comes down to CDNs, being able to move your content closer to your users. The messaging solutions, being able to deploy aggregators of those messages, so people are connecting to local systems to get messages rather than going right the way back across to the main data center again. Keeping the user informed. So this is more of a sort of usability thing, I guess, really. But if the phone is having to do a lot of work on a mobile device, if it is having to download a very large data set, or if the server side is having to do a lot of processing to build that response, just keeping the user informed and something moving on the screen. This counts double for financial apps where you're simulating a connected data model across a disconnected HTTP traffic, essentially. So you definitely want to inform the user if something is disconnected so they can take action when it reconnects again. And that deployment model that we talked about in terms of CDNs, enterprise messaging providers, that's essential to get that right for the data type of application that you're using and the type of application that you're using. So just in terms of takeaway points here, just to really kind of try to pull together some of the things that we've discussed. So it's important that you test your mobile apps from a client-side performance perspective and a server-side load perspective. And those two, when combined, kind of build a picture in terms of how your app is performing and how your system will perform at load. One of them will provide you with some information, but won't provide you with everything you need to know. Define those NFRs up front, build them into the application, and ensure that they're met. Test your system as early as you can. Don't wait right until the end, until it's absolutely complete and ready to go live. As soon as you start to develop a system, consider performance test tooling and make sure that the tooling that you're going to select is able to test the technology that you're using to write the application. And the fact that no one team can fix this, really. In order to produce an app which is optimized for performance, everybody needs to be involved. So you need the dev team needs to be involved, dev teams creating the client-side code, the server-side code, the infrastructure guys, the deployment guys, all of whom need to be involved and all of whom need to understand each other's requirements, because one team can make a difference which can make life easier or life harder for upstream or downstream teams required to actually put the solution together. So a good example of that is, for instance, if the app isn't defined in such a way that it is able to be deployed across a CDN, for example, so that precludes you from being able to do that. Another classic example, dev teams not building automation IDs into code, for instance, so when it comes to test automation, that makes the life of the devs much harder. Easier to manage if you're sat in the same room or if you're sat in the same as an internal dev team, much harder to manage if it's another vendor that's producing the app for you. And the final point, so in the testing that we've done, what we find is that it's actually more important to have an application which performs well from a messaging perspective, which is optimized, actually more often than the actual choice of technology you're using yourself. So you'd expect still the fact that a native app will be quicker than a hybrid app, and whilst that is the case, it's possible to design a hybrid app which actually performs much faster than a native app, and a native app which through suboptimal choice of technology and suboptimal choice of messaging actually ends up been slower than the hybrid app. I've seen this a few times. I think that kind of draws us to an end, really. So if anybody has any questions, if you'd like to fire them in now, we can take a look at that. I really would appreciate any feedback that you'd like to provide on this in terms of level of detail, too much, too little, too few slides, too many slides, and really sort of anything else that you would like to come out of this. I mean, some of the topics we touched on are really webinars, white papers in their own right, just by themselves. So we've had to cover quite a lot of ground and skate over at a quite high level. But if anybody does have any further questions, my email's there, or alternatively just reach out to me on Twitter and we can go from there. So we'll just wait a few minutes for any questions to come in, and we'll draw that to a close. One point, so the this webinar, Adele is going to essentially pull this together and send out a link to everybody so they're able to look at that, and they'll be able to review. So question, what are the unique differences among client-server, regular web, or a mobile native app or mobile web app for performance testing and ensuring performance? Thanks. Okay, so the differences are, so if we consider first, let's go with just a standard sort of client-server application, by which I'm assuming you're meaning a fit client application. So a fit client application, it's running on normally on a desktop machine. Chances are you're normally connecting over a network which is going to be wireless or it's going to be wired. So a lot of the issues around connecting with mobile data comms go away. One thing we haven't touched on, but with mobile apps, you need to be mindful of power consumption as well in terms of how you're using the wireless. The fact that you have a finite amount of resource on that device and a finite amount of power in it. A lot of those issues go away. But in terms of server-side performance testing, the approach is exactly the same. You capture the traffic, you record the journeys, you correlate, you parameterize, and then you play them back in a transaction volume model. From a web app, again, it's quite similar from a server-side performance testing perspective as for a client. The good thing about using it with the standard client-server architecture is that in terms of the devices that you're testing it from, you only have really one or two to consider. With a web app, you have browsers to consider, different browser types. If it's a rich internet application, you've got to be mindful of the version of Silverlight or Flash or whatever it's using as well. So that builds out quite a hefty matrix in terms of tests that you need to run on it. From a mobile native app, again, with iOS, you've got a fairly limited number of devices. With Android, it's significantly more. So the server-side performance testing approach is pretty much the same. You need to be less careful around how susceptible your application is to mobile data comms if it's clients as well. And with the web, you need to be mindful of internet traffic and optimizations that need to go on there and different browsers, but not. Yeah, I think that's probably the way to think about it. So really, in terms of complexity and in terms of considerations, client server is easiest. You then go into web in terms of the number of options you have to test, and then mobile on top of that. Somebody's asking about simulators and emulators, whether they're a good approach in terms of recording timings on them. I think the key point is that what they were able to provide is a decent benchmark for regression testing, so you're able to see whether performance has improved or regressed between releases, and obviously they're very valuable from a functional point of view. But in terms of being able to say, running on this particular Android emulator, for instance, how does that compare to this particular Samsung device? And it's not going to be able to answer that question. But it can be valuable, but again, it needs quantifying. And again, if you quantify with a slow device and a fast device, that'll give you a couple of extremes, and then you can benchmark your emulator performance against that and get an idea of what you're seeing. Okay, I think that's. Well, I'd just like to say thank you, everybody, for attending. So you have our details there, and this presentation will be made available to you shortly. Thank you. Thanks very much.